Here's a sample problem and how to calculate potential energy stored in a loop that is placed in a magnetic field. And so we have a loop with 3 amps of a current. The loop is at 25 degrees with the magnetic field. Let's do it like this. So I'm going to draw a picture here. Here's the loop. Let's say that the current comes out of the page and then flows like this and goes into the page. So that this is I, out of the page, flows down into the page. And the magnetic field is at 25 degrees with, and so first of all, let's state what this I is. I is given to us as 3 amps. And then we have that the loop itself is at 25 degrees with the magnetic field. So let's draw the magnetic field. Let's say that the magnetic field just points like this. This is B. And let's say that the angle here is, let's say that the angle is, that this is the angle, 25 degrees. So this is 25 degrees here. And the magnetic field itself, B is 2 Teslas. So I'm going to put here B equals 2T, 2 Teslas. We have the area of the loop. A is 20 centimeters squared. And so that would be 20 times 10 to the minus 4th meters squared. And the unknown, let's state the unknown. The unknown is, what is the unknown? The unknown is the energy. How much energy is stored in this arrangement? So potential energy at this instant, what is that? If the loop is initially stationary, how fast is it rotating when it turns through 10 degrees? So we'll come back to the second part of it. We have the mass of the loop, so I guess we'll add that here. Mass of the loop is 20 grams. So 20 grams is what we have. All right, so let's first calculate the potential energy at this instant. So potential energy, let's go from this equation. It's U dotted with B, which amounts to being I times A times B times the cosine of the angle theta. So let's plug in what I have, the minus, and then I have I is 3 amps. I have 3 times the area, which is 20 times 10 to the negative 4th, times the magnetic field, which is 2, times the cosine of, so I have to figure out that part. A vector points like this, 90 degrees to the surface of the loop, and so I can fairly easily figure out the actual angle theta. Theta is this here, so this is my angle theta, and I can write here that theta is just 90 minus 25. 90 minus 25, and so that's going to give me 65 degrees. Right, and so I would put 65 here. Then whatever I get out of this expression here is going to be the potential energy that I have. So P equals, let's calculate this out. So we get 5 times 10 to the negative 3rd joules. Okay, this is what I have, the initial potential energy. There should be negative. I should keep that negative. So here's minus. All right, so I'm done with the first part. Now the second part is, if the loop is initially stationary, let's maybe call this first part. Here's the second part. The initial speed is 0. This thing is not moving, and so also, actually that's almost meaningless because this loop is not really, doesn't have any velocity except for the angular velocity. So let me get rid of that and write here instead omega. I is 0. Initially it is stationary. How fast is it rotating when it turns through 10 degrees? So what is the final speed given that it will rotate through the angle of 10 degrees? All right, so what I can do is I can do the following. Energy is conserved here. There are no losses of energy as this loop rotates. So this loop is going to rotate here. Let's see which way will this thing rotate. So if magnetic field points in this direction, this comes out. So the forces act like this. These are the two forces, and so this thing is going to rotate in this direction. So as this loop rotates, it rotates without any friction, and because there is no friction, and then energy here is conserved. And so what I'm going to have is the initial mechanical energy is equal to the final mechanical energy, and I have both. Initially, I have only potential energy present, right? Potential because the kinetic energy is 0. Kinetic energy is 0 since this thing is not moving at all. And then the energy in the end is going to be some other potential energy final plus kinetic energy final is what I'll have. Now the initial potential energy, well, that's just this. So I have that. I have that initial potential energy. That's my initial potential energy. So I can write here, this is minus 5 times 10 to the negative third joules, and then equals, I have to figure out the final potential energy. And as far as the final kinetic energy is concerned, well, that's just going to be half times I times omega squared. And come to think about it, do I have any dimensions of this? I have the radius. Oh, okay, well, I don't have the radius, I have the area, but I can work from that. All right, so what I need to do is figure out the potential energy final. So maybe I'll do it here on the side. Final potential energy would be, well, would be minus I times A times B times the cosine of the angle theta. And let's plug in some things for this. So this would be minus 3 times A, which is 20, times 10 to the minus 4th, times the magnetic field, which is 2, times the cosine of the angle. Well, I'm moving through 10 degrees. Now, initially I was at 65. Now this thing rotates farther so that the angle between A and B is less. Keep this picture here in mind. So if I start at 65 degrees here and I continue to rotate through 10 degrees, then I'm going to end up at 55. This is going to be 55 degrees. So now I can calculate this, and that's going to be the final potential energy that I'll have. So let's calculate this. So this is minus, and we have here 6.9 times 10 to the minus third joules. All right, so I have the initial potential energy, I have the final potential energy. Okay, so let's do let's go back to this other equation here. So what I have is, let me actually state it this way. So I'll have the initial potential, actually, whatever. So I have minus 5 times 10 to the negative third equals minus 6.9 times 10 to the negative third equals half I omega squared. I'm sorry, this is a plus, half I omega squared, and then I bring this to the other side, and the difference between the two is just going to be plus. So I end up with 1.9 times 10 to the negative third equals half I omega squared. All right, so now I have to, so I'm almost done. I just have to now find an expression for the moment of inertia of this loop. All right, and at this point I'm realizing that you could do it. Moment of inertia, I think moment of inertia, I just did it on the side, and I cut it out of this video, but the moment of inertia of this whole loop about the axis of rotation, it's something like 1324 ml squared, and given the fact that you know the area A equals L squared, you can figure out L, and you have the mass is given as 20 grams. You can finish this problem. The only thing is that there's no need to play with the moment of inertia here. So what if we get rid of this and just say moment of inertia is 20, and then let's make sure that this were kilograms meters squared, and let's just go with that instead. So to finish then the problem, I'm changing the problem. In other words, what I'm doing here is I'm looking at the problem here. I'm doing is I'm saying nope, and I is equal to 20 kilograms times meters squared. So we're going to be given it a substantial moment of inertia, and we end up with 1.9 times 10 to the negative third equals half times 20 times omega squared. That's just, of course, 10. You divide this thing by 10, you end up with 1.9 times 10 to the minus 4th equals omega squared. And so out of this, we get omega, which is 1.4 times 10 to the negative second radians per second. That would be the speed, and so this will do. If for the other simple problems that I gave you, you run into something similar, that is, if I give you mass in the other problems on the worksheet, and I think I probably did, just turn that mass into moment of inertia. So instead of grams, just turn that into kilograms times meters squared, and use that as the moment of inertia, and then calculate whatever you need to calculate. I think that'll be fine. Okay, so here's a simple problem on how to calculate the potential energy of a loop of a current I in a magnetic field, and how to use it to figure out what this loop will do if placed in a magnetic field.